Thank you, everyone, for joining this session. My name is Hamid Akhtar, and I'm part of Percona's Postgres engineering team. Today, I'm going to discuss Postgres replication and the conflicts and how we can potentially avoid some of those conflicts. At Percona, it's not just about Postgres, but we offer MySQL, MongoDB, and we have a monitoring and management tool as well, the PMMs. A little bit more about myself. So I've got more than 2 decades of professional software development experience. I'm currently the engineering lead for Postgres at Percona, where we've been working pretty aggressively on a query observability extension, pgstat monitor, which is kind of like an enhancement to pgstat statements, if you're familiar with that. It gives you a lot of query performance insights from a very different perspective, which we believe is very useful. Other than that, with my almost 2 years at Percona, one of the things that I really like about Percona is an amazing and very warm, welcoming work culture. So that's been one of the standouts for me at Percona. Prior to Percona, I was part of Hygo and Enterprise DB. I guess Enterprise DB needs no introduction. And really, at Hygo, I was working on foreign data wrappers and an in-memory access method for Hygo database. At Enterprise DB, it was more about configuration management, where I was leading the team for Postgres installers. And you might have used the Windows, Mac OS, and back in the days, the Linux installers, or perhaps Solaris or HPUX installers as well. In case you need to reach out, my contacts are the email, LinkedIn, and my Skype handle is here. More active on LinkedIn than Skype, so feel free to get in touch with me. Other than that, if you want to reach out and contribute or look at pgstat monitor, we've got an open source repository. Everything at Percona that we do is completely open source, no strings attached, with a very liberal license. So everything is out there for you to see or contribute or explore. So starting with why I think I felt that I need to pick up a topic about Postgres replication or the conflicts, because one of the challenges I saw was I could not find enough information out there about the replication conflicts, how those could occur, and how we can actually track or understand the server response to such a scenario. So replication is no different than any other system where you start with an optimal configuration. You tune that setup for your workload, for your needs, and then the entropy degrades that performance over time. In database terms, that's really queries. The incoming queries change the state of the system and eventually degrade it to a less performance system over time. So that's why query monitoring is imperative. So looking at query performance, the execution patterns, the challenges with queries, whether they're running for an excessive amount of time beyond their expected age. So monitoring is a critical part of that. And that is really helped by almost, I think, 50 or more views, statistics views that are offered by Postgres out of the box. A lot of details, a lot of statistics about pretty much everything that you may need to know, including the most famous pgstat statements extension, which has in PG15 more than 40 columns, pretty much all numbers, some date timestamps, but quite a few numbers. And to make sense of those numbers or stitch a picture together from these statistics, the plethora of statistics you have here, that becomes a challenge on its own. Finally, it's about once you have an optimal setup, the monitoring is there, the analysis, the ability to analyze the performance is there. You want it to be a fail-safe or a self-healing kind of a setup. So that's where the failover or switchover handling comes in, where you can use anything like a PG pool or Petroni or any other solution you may wish to use. But one part of that self-healing and one part of that availability is to ensure that the risks are mitigated or at least assessed upfront. And that's where the replication conflicts come in a replication environment. So in this talk, we're basically going to start with the key components of a replication environment. It starts with the locks, followed by wall. And then we're just going to dig into the history of how replication got implemented. We're going to look at the conflicts, and then we're going to track into the server side of things, how server responds to these things. The role of locks is essential because that's where the multi-concurrency comes in. Wall is obviously a key component of that. So a lot of these things we're going to discuss further. Starting with the locks, so Postgres has lightweight locks, but there's a lighter version of those locks. In terms of locks, there are user-facing locks that you use in queries, or they're implicit or explicit locks. So some queries, for example, would lock rows or tables or other objects. Then there are explicit locks where you acquire an explicit lock on an object. Also, there are advisory locks, which are really integers that you lock, and it's the responsibility of the connection or the backend to release it while the others are waiting on it. But we're more concerned with the internal locks, and there are the three types of locks: the spin locks, the lightweight locks, and the regular locks. Spin locks are really the lightest weight locks, really. So they engage the process, the competing process, in a busy waiting loop. So when a lock is acquired, the other processes are really just busy waiting. So it's effectively consuming resources. With the expectation that a lightweight lock, a spin lock is acquired for a few dozen instructions at most. So the span of this lock acquisition is very short, and it's not meant to be operated on, for example, on huge functions or functionality should be executed. It's primarily to protect data. So your variables, your atomic variables, they have internal spin locks. You have other data structures which you want to guard from multiple or concurrent updates. So that's where the spin locks will come in. There's no nicety with these locks, so they don't have deadlock detection, they don't have release on error. So that's the responsibility of the code or the responsibility of the owner to just release those locks in case there's an error. So that's, and then in terms of its timeout, a lock, if it's not released, would be automatically released after a minute. But in terms of the lifespan of these locks for which they should be acquired, this is a huge amount of time. A minute is huge because you're just meant to execute a few instructions. Lightweight locks are used to control data structure. So they're a little more kind of extravagant as compared to spin locks. Just to give you a comparison with how the lightweight locks or the spin locks are used, pgstat statements as an extension and a small code that if anybody would wish to dig into, when it's updating a variable or a counter, it will use a spin lock. But when it's searching a hash table for a list of entries of the queries, it's going to acquire a lightweight lock. Lightweight locks can provide option for read locks and for read and write locks. So you have read lock and exclusive lock on it. Exclusive lock obviously is when you want to update a data structure, and that's when you acquire an exclusive lock. But lightweight means that you don't block the readers. So they're good in that sense. They're automatic release on error, so that's one benefit. Once we're into actual execution of functionality, we would want some niceties here. There's no deadlock detection here either, so not that nice, but good enough to release it. Again, they're awarded in the order in which the processes arrive, so there's actually a queue here. The regular locks or the real heavyweight locks are the ones which we're really concerned with in terms of replication conflicts. They support all different types of lock modes and table semantics. They have deadlock detection. They're monitored by a resource manager. And all user requests are really with these locks. So they're as heavy as you can get in terms of locks. And write-ahead logging. And it's basically at the core of replication, and your standbys are really catching up with the primary server, and the changes are happening there. And the mechanism or the vehicle through which they track those changes are the write-ahead logs. It was actually introduced in 7.1 back in 2001, so it's been out there for 22 years now. Prior to implementation of write-ahead logs, the backend processes were actually writing the data or the transaction data or the page directly onto the disk, which meant that there were multiple writes and a lot of excessive writes. If you just want to update one tuple and another connection wants to update the same tuple or the same tuple or a tuple on the same page, the page would be dumped multiple times. So this led to pretty bad update and insert performance for Postgres for 7.0 and earlier versions. Write-ahead log is essentially what guarantees the durability in the asset compliance. And it's really, in terms of the durability, it not just provides a mechanism, but it enhances it by some changes that I'm going to discuss on the next slide as well. So the durability is provided by write-ahead logs. Previously, it was called Xlog in version 9.6 and below. And people obviously don't like logs in their file system, and RM minus RF logs was a good practice by a lot of people. That led to quite a few issues. Version 10 and beyond, it's now PGWall, which is a good usability enhancement. So it protects from accidental deletion of this. And it's not just about relations, it's also about indexes. The two things obviously require persistence, and hence it's imperative that the durability of indexes and the relational data is maintained. So this now improves performance pretty significantly as compared to earlier implementation, because now, one, you're just updating one file sequentially, which means that it can be optimized. The second is that a lot of things can be grouped together and then flushed onto the disk. So that's another part of it. And then the write differential that you're now writing, you're no longer writing the entire page. You're writing a few bytes, which again is a significant enhancement, and it obviously leads to an improved performance and response times. The other feature that was introduced as part of WAL in 7.1 was checkpoint, which allows, which basically clears up the dirty pages or flushes them onto the disk in simple terms. And with checkpoint, the additional durability that WAL now provides are full page image writes. This is again a durability enhancement or feature because it guards against any unfinished page writes in case of an OS crash. So a full page is written once after a checkpoint. If a page is dirtied or if something is changed in a page, the entire page is dumped into the WAL. So now you have the complete copy of that page that you can refer back to avoid any page corruption issues. The WAL file name is always, to me, looked a little odd. A lot of numbers, a lot of digits in there, hexadecimal digits, but it actually comprises of 3 8-pair digits, with the first one defining the timeline, and the next two are the WAL file and the location within that WAL file. The reason why the last 6 digits are highlighted, because they effectively define a size of 16 MB, which is the default WAL segment size when you do in a DP. So you can change it, but that's the default. With reference to WAL and how the changes are tracked within WAL are through lock sequence numbers. In Postgres, internally, this is PG, the data type is PG LSN. And it's an 8-bit unsigned integer, and you can consider this as really two 4-byte integers separated by a slash. It's a very, basically, and it's a very insightful data type because it can provide you a lot of details in terms of how much data is being written to wall. You can get the current LSN location through the PG current wall insert LSN, but you can also get the file name and the location of that LSN within a file. So you can actually track, for example, once you insert a tuple in a relation, how much wall data has been written. And that wall data obviously then leads to an understanding of how much bandwidth or how much data would be shipped across to standbys. So the function that you can use is PG wall file name, but you can also append _offset to it, and it will provide you not just the file name of an LSN value, but also the offset of that within the file. So let's look into how the replication functionality evolved into Postgres. It's actually pretty interesting. The first attempt or the first piece of code that if you track back, you'll find is from 1999, when there was replication for distributed databases. But the real implementation came in 2006 with 8.2 release, because now this was basing on the wall infrastructure. So it was utilizing the wall files rather than the previous setup. So this is a complete rewrite. What it introduced was the concept of continuously archiving and continuously recovering. The primary was continuously archiving and saving that wall data and shipping it onto the standbys, whereas the standby was in a continuous recovery mode and just replaying or redoing those log files. It was asynchronous, and this was a file-based log shipping. So really, the primary was actually accumulating a lot of changes before it was shipping it onto the standby, which meant that this was, there was potential for data loss because the standby was not up to speed with the primary, and it didn't have all that data because it was just being packaged on the primary server. There was one option that could reduce that, and that was archive timeout, but still that wasn't good enough. This was actually not high availability solution, but this was more of a disaster recovery, as the standby was warm and it wasn't really accepting any connections. So the temperature was just increased a bit with 9.0 release, so we got the hot standbys. So the transition from warm to hot was now that we could query. But it introduces two processes. There was wall sender and wall receiver. The responsibilities were pretty well defined. In terms of wall sender, which was on the primary, it was responsible for writing the wall files onto the disk and shipping them onwards to the standbys. Whereas the wall receiver was responsible for a couple of things. It was responsible for receiving that data. It was responsible for basically copying it into its buffer and then flushing it onto the disk. So it was maintaining connection. It was flushing it onto the disk because you can't really rely on disk cache. In case of failure, that may lead to data loss if the cache is not battery-backed unit. So there were those challenges as well. The first couple of functions were introduced to track replication in 9.0, and the two functions were receive location and replay location. Although this was a significant enhancement since 8.2, but still this could take a second, which meant that you could still end up with data loss, and this remained asynchronous. So this was immediately solved in the next release of 9.1 in 2011, where now you have the synchronous streaming replication. This was more of a performance versus data integrity trade-off, where you're now synchronizing with the standby rather than just doing an asynchronous communication. So there were stricter data integrity guarantees now with synchronous standbys, and there were a lot of configuration options introduced where you could specify a quorum or you could specify priorities within the standbys. In 9.4, you had the logical replication come in as part of the decoding of WAL for replication. As a focus of this talk, I'm going to primarily discuss the physical streaming replication. So going to look at replication catalogs and configurations. Essentially, the two views that are really of concern are pgstat replication and pgstat WAL receiver. Stat replication is on the primary, whereas the stat WAL receiver is on the standby. On the primary, stat replication contains one row per WAL sender, and it contains a lot of information in terms of the LSNs, what LSN has been sent to a standby, what has been received or flushed to disk, and what has been replayed. So it's maintaining or it's tracking those changes. There are time intervals as well. The only challenge with this view is that it's essentially a join between pgstat activity and WAL sender functions, which meant that this information would not persist would not persist if the connection or the standby connection is terminated. Stat WAL receiver provides pretty much similar information. It provides you with the connection information, but all of this is from a standby perspective, which is maintaining one connection to the primary server. It also tracks replication slots, a replication slot that it's tracking. In terms of conflicts, unfortunately, there's just one view, and that view is pretty minimalistic as well. So it has 7 fields. One is a database ID. There's a database name. And then there are 5 counters. And that's all the information we have in terms of conflicts within the database. There's also one field in PG-stat database, and that's just an accumulation of conflicts, so not a lot of insightful information here in terms of out-of-the-box statistics that Postgres provides for conflicts. I think one of the things that people generally find a little complex with Postgres are a huge number of configuration options, which is pretty tricky, and tuning becomes a challenge then. There are a huge number of configuration options, as you can see, just for setting up a replication. But I think once you start looking into these, they're actually kind of associated with one another in some way or form. The 3 different types of servers that are listed here, primary server and standby, is pretty clear. Sending server is a server that's shipping log files onwards. So that could be your primary server. It's always a sending server, but that could be a standby in a cascade replication, which is responsible for transmitting the WAL files onto another standby. In terms of the configuration options, you have max WAL senders. That's the number of WAL sender processes that can be present on the primary server. With this configuration option, what you really would want is to keep it slightly higher than what your max would be. This is connection. This tracks connections, and connections are not immediately recycled. So in case a standby is disconnected, it may and it wants to reconnect, the connection may not have returned back yet. It has a timeout, so by default that's 60 seconds. So you probably want to just make sure that's slightly higher, otherwise you would end up with a standby that's trying to connect and can no longer connect with the primary. Then there's WAL keep size. I'm just going to discuss the ones in orange, which I believe are more relevant. WAL keep size is, in terms of megabytes, the maximum amount of WAL size that would be kept on the sending server for replication purposes. WAL sender timeout is, again, the timeout, and it's associated with WAL sender max wall sender as well. That's a timeout after which if a replication connection is inactive for this time, it will be terminated. On the primary, we have synchronous standby names, the vacuum defer cleanup age. Synchronous standbys is kind of a list or a configuration of standbys for where you can specify either a set of synchronous standby servers, or you can specify a priority of those, or you can specify, say, just a subset of those through either through some of the qualifiers that you can put with the name. So you can say, for example, 3 out of 5 standbys, or any of these standbys, and the priority order becomes the sequence of the listing of names becomes the priority order. Vacuum defer cleanup age is one of the things that could potentially cause conflicts in replication. That is the number of transactions that the number of transactions that should be retained or should not be cleaned up on the primary server by the vacuum or by hot updates. On the standby, you have max standby streaming delay. That is one of the configuration parameters that would cause a replication conflict to arise. Wall receive a status interval and hot standby feedback are the two other parameters. Wall receive status interval is the time or is the interval after which the standby would be reporting its updates in terms of LSNs, the replays of those LSNs to the primary server. Hot standby feedback is again a number of transactions that are it's basically the insights into the queries that are being run on the standby server, and that would cause the primary server to hold back cleanup of that data, and that could lead to database bloat in general. So a physical streaming replication has one primary and standby. So where would the replication conflicts come in? The replication conflicts are never there on the primary server. They're on the standbys. So primary has no challenge at all, so to speak. It can do read and write, and it's free to do whatever it wants. On the standbys, you do have an issue because it has a higher priority process, the wall receiver process, that's responsible for receiving the data from the primary server, and it's also responsible for redoing those changes on the server itself. And that high priority process in the back end is where the conflicts on the standbys would come in, and that's when you need to effectively kill some of the backends. Why would this be the case? Generally, the multi-version concurrency control is at the heart of all of this, but more so are long-running queries. Long-running queries are not just a problem in replication, but in any case, long-running queries are a huge challenge, whether they're prepared statements or whether they're just ordinary statements being executed on the server. With prepared statements, it becomes a bigger challenge to be able to track time or the duration of those prepared statements. So one thing that I suggest with reference to prepared statements or orphan prepared statements are that you kind of name them with an expiry time frame, so that a backend process can then monitor them and terminate them because they wouldn't be associated with the connection. So replication issues are pretty common. This is one survey that I had internally at Percona with the database users and DBAs. And although the number of respondents isn't great, but looking at that number, still 5 out of 9 people responded that they've experienced replication issues, and that's significant because some of the people out of those 4 did not even had experience with replication in Postgres. The kind of replication issues that people have faced, there is replication lag, obviously, no surprise there. Loss of wall files, I guess no surprise there as well. Loss of replication slots, that's not a surprise either. But if you look at the number of conflicts that are there, you have the lock conflicts, you have the snapshot conflicts, buffer, pin, and deadlock are a little rare, but they're conflicts that can be potentially avoided. Replication slots, obviously, you can't do much. You couldn't do much previously. You can now kind of hack it through Petroni now with the, some of the recent changes that they've introduced. So the only view that provides some insights into the replication conflict is PG stat database conflicts. And it's tracking 5 different kind of conflicts. It's tracking a tablespace conflict, which is effectively the temp tablespaces. They're dropped on the primary server, and that could lead to an issue on the standby. Again, it's a very rare scenario. How many times are you going to drop a temp tablespace? But there are instances where people do that. Buffer pin is again a pretty rare case where a pinning of a buffer really in the Postgres terms is effectively a backend accessing a page, and they just want to make sure that it does not disappear under their feet. So it's they increase a reference count, and that reference count for a page or a buffer greater than 1 indicates that it's pinned. And that's when, say, again, another backend process like the hot chain pruning process would run into a conflict because it wants to acquire an exclusive lock here. Deadlocks are not that common either, but what we're really going to look at are locks. So querying a table on the standby, and it was remotely altered on the primary, leading to a conflict. So in terms of altering a table, it wants, so the wall receiver process would want to acquire an exclusive lock. A query is holding either a shared lock or an exclusive lock, and that is going to cause an issue. Snapshot is the case where the row versions or the dead row versions are going to be vacuumed out on the primary, and the same process is going to be repeated on the standby, whereas on the standby, again, the lock could not be acquired. So there are certain things that, certain tweaks maybe that can help eliminate some of these conflicts. So what I looked at was a PG 15 and 14 as well prior to this. And I saw how I can actually generate the lock, these conflicts, and how the server would respond once these locks are generated. So understanding from an internal perspective of the server behavior does help in kind of really understanding the behavior. So let's start with the lock conflict generation. Starting on the primary server, let's create a table, fill in 100 rows. On the standby, let's start a transaction, and let's just query that table. I've just queried that table, and I'm not really actually using it in any way, but the resource manager would track that this transaction is touching this relation, and it's going to still maintain a lock on this. Although there's nothing useful happening with this, there's no isolation level specified as such, but still it's still going to maintain a lock here. Dropping that table on the primary would, and then waiting on the standby. The standby has a max standby streaming delay, which is 30 seconds, I believe, by default. So it's going to wait for that, and if you try to requery, it's going to come give a fatal error, cause a disconnection, and provide you with a very specific error. That terminating connection due to conflict with recovery, user was holding a relation lock for too long. Looking at the replication, looking at the database conflicts view, all you'll see is an incremented value of lock conflict by 1. I think one important information is that the information in this view, stat database conflicts, is ephemeral. So a restart would cause loss of this data, so it does not persist across restarts. So looking at how internally the server responds to such a scenario and what it's actually trying to do. The moment it receives a wall record, what it really needs to do is it wants to redo that on the standby. So from accepting of that data to now trying to redo that, in this particular case, it wants to acquire an exclusive lock on the relation. It goes through a huge code, a lot of different functionality just to assess and acquire the lock. And then what it finds out that there are other backends that are holding back locks. So it tries to then identify what other backends are holding back those locks. It gets their PIDs, and it then waits based on the max streaming delay option. So it'll wait for that, and after that, it's effectively going to ask all of those backends that are still there, that are holding back the locks, it's going to ask them to terminate. So with that termination message sent across to all those backends, they have no option but to just terminate and end that process. What can help here? Obviously, lock monitoring. If you're not monitoring these locks anyways, that's a key to understanding whether locks are being held beyond their expected age. And joining PG stat activity and PG locks based on the PIDs would give you some information in terms of what application are holding back locks, whether and if there are any queries that are specific that need attention. Aging transactions are again a challenge because they're going to hold back resources, they're going to hold locks, and that is going to cause an issue for. You might want to tune the max standby streaming delay based on your workload, whether your queries are expected to last for a particular duration that you have assessed. So you might want to tune this parameter. Again, and also you also would want to ensure that the transactions are not touching any relations that you don't intend to use. Just so cleaning or cleansing of that is also a key because that would reduce the locks on those relations in the transaction. Looking at a snapshot conflict, a little slightly different mechanism to generate this. So creating a table, filling it with 100 rows, declaring a cursor, and just start fetching from that cursor. And then you clean up a few rows on the standby, on the primary, and you run manual vacuum. We're not waiting for the auto vacuum to run. So in this particular case, the manual vacuum instruction was initiated, which meant that the max streaming delay was completely ignored on the standby. Because this was a manual instruction that had to be executed or replicated on the standby. So the next fetch immediately causes a termination, again with a very specific error, telling user exactly what the problem was. The user query might need to see row versions that must be removed. In terms of what we have in the view PG-STAT database conflicts, it's just again an increment of 1 for the snapshot conflict. In this particular case, the behavior is slightly different. So starts like the lock conflict with XLOC processing, but in this particular case, it goes into the excess methods. It needs to clean up, and the relevant routines would be executed for cleanup. But from there onwards, the behavior is pretty simple. It identifies the conflicting backends, gets their PIDs, and it tries to, and ideally it would wait, but in this particular case, it does not because there was a manual vacuum instruction. What you would be interested in this particular case are vacuum deferred cleanup age. That's not honored if you're running manual vacuum. Hot standby feedback, that eliminates or that reduces the risk of query cancellation because of cleanup operations. Hot standby feedback works on cascaded standbys as well. The feedback is provided through the cascaded infrastructure where it would say it'd be passed on to the standby, would then pass it on to on further. So just to close off, it's to start with, any setup would have to be tuned for your specific workload. So there's no one solution that fits all. And pgstat replication, wall keep size, network latency, wall sender timeout, those are the things that you would want to keep an eye on. With pgstat replication, the LSN information that's being provided would tell you some insights into the wall size that you need to maintain. The timeout for wall sender, again, that really depends on your network latency. In terms of understanding the patterns of replication or the lag patterns, that information again is ephemeral and it changes. There's no persistence or there's no pattern or analysis like you would have with pgstat statements where you have standard deviations, min, max values. In this particular case, you don't have any of that. All you have is a list and certain values. There's no kind of performance pattern that you can identify and track. So you might want to make this information persistent over time and see how the lag increases or decreases, whether it's going beyond a certain threshold at instances, or whether it has the ability to catch up with the primary at some point in time. Again, long-running queries are a must-have. If you're not tracking them just in your environment, they're going to lead to all sorts of issues, whether that's bloat or whether that's replication conflicts, potentially. At Percona, one of the values that we evangelize is freedom of choice, and that's out there with our everything open source, everything within open license. So no LGPL or GPL license. It's all out there for you to pick up or contribute or work together. That's all. Thank you so much. Feel free to reach out to me in case you need to discuss anything. Thank you. Sure.
Well, I have a problem with replication. I'm inserting millions of tuples to the primary database, and there's a big lag while sending the wall stuff to the what do you call it?
The standby?
The standby. So my question is, do the wall keep size setting might help me, because it's writing a lot, so that might be affected.
Well, there are a lot of parameters that would need to be investigated, but wall keep size is just about maintaining enough wall data on the primary so that standbys do not lose track. So they have something on the primary available to them. Once a standby or the lag goes beyond that, it's no longer recoverable. So it has to be basically put down or reinitiated through other means. But wall keep size wouldn't help in this case. I think it's more to do with your maybe network infrastructure, or whether that's introducing lag, or whether you have other problem.
It's, for example, it's taking too long to copy the wall to the second.
Sure, we can discuss in more detail after this I've got. So we'll get into that. I guess that's all. Thank you, people. Thank you, everyone.